For a very long time, humans have imagined what life would be like on other planets. And when the golden era of exoplanet discovery began, the possibility of Earth 2.0 or the planet's sibling saw some silver lining. Searches have so far turned up nothing, prompting scientists to use their imagination to find another potential planet for life in the cosmos. Now we can answer that question. Thanks to the James Webb Space Telescope, the most potent telescope in the world, we will have new tools to respond to the age-old query of whether or not there is life outside of Earth. So, join us as we are going to explore James Webb's startling discovery of city lights on Proxima b, which alters everything. With that said, let's get started. So far, we are only aware of life on Earth. Since the beginning of civilization, people have wondered if there is life elsewhere in the universe. To carry out such interstellar searches, American astronomers Jill Tarter and Thomas Pearson founded the Search for Extraterrestrial Intelligence (SETI) project in 1984. The non-profit's objective is to gather an extraterrestrial radio message. Because, compared to other radiation types, radio waves are less likely to be dispersed or absorbed. They are more likely to be detected by the 42 radio telescopes that make up the distinctive Allen Telescope Array in the California and Cascade Mountains, because they can travel further. But in the last 30 years, no verifiable extraterrestrial signal has been discovered. The James Webb Space Telescope, JWST, the largest telescope in the world, which is floating about 1 million miles from Earth and equipped with incredibly sensitive detectors, will study a variety of distant, undiscovered planets orbiting far-off stars. After that, the search was aided by the successful deployment. No planets other than those in our solar system were known 20 years ago, but since then, more than 4,000 more planets, sometimes known as exoplanets, have been discovered circling other stars. According to NASA, the cosmos may contain billions of exoplanets. The earliest signs of life outside of our solar system may be found in extraterrestrial plants. A mixture of red and infrared light reflected by plants was identified by the device when the Galileo spacecraft rotated its instruments back toward Earth while in motion. This was a clear indication that there were plants present. For instance, if there is an Earth-like planet covered in rainforest, it should have a strong VRE signal that is easy to find. The exoplanet atmospheres of distant Earth-like planets in the habitable zone orbiting stars will be measured by the JWST for any major signs of life. When sunlight crosses an exoplanet star, the JWST may be able to detect it when it enters its atmosphere. Spectroscopy would then be used to discover the light's missing wavelengths. Atoms and molecules in the atmosphere absorb certain wavelengths, creating a characteristic fingerprint that the JWST can identify. This method allows for the discovery of the hemisphere's composition and the deduction of the possibility of life. It seems likely that life may exist on Earth-sized planets with atmospheres that are similar to our own, with an abundance of oxygen, nitrogen, and carbon dioxide. Additionally, it could be feasible to detect technological life by looking for elements that don't naturally arise. Chlorofluorocarbons, CFCs, which were created for use in cleaning supplies and refrigeration, would probably be noticeable to aliens from a distance in maintaining our atmosphere. If the JWST found CFCs in planetary atmospheres, that would be a clear indication of civilization. Exoplanet life may not even somewhat resemble life on Earth. Even life on Earth, like some creatures that move very quickly, can occasionally seem strange. This is a category of organisms, usually bacteria, that can endure environments where other living things would not be able to. Some of them can withstand heat up to 250 degrees Fahrenheit. Others can guarantee low temperatures of -4 degrees Fahrenheit. Others can be found on Earth in places where we would not expect to find any life at all, such as species that can survive in strong acids with pH values below 3. However, it would be sensible to start looking for planets that are similar to Earth first, since they're more likely to support life than worlds with incredibly high or low temperatures. Prime candidates could have temperatures that allow liquid water to exist in their cells and circle a stable star. Temperature allows liquid water to dwell on its surface. The classification of our Sun as a yellow G-type star. However, stars in our universe are rarer and often have shorter lifespans. The likelihood of studying planets spinning around red dwarf stars, which are more common and have lower luminosities and temperatures than the Sun, is higher. There is more time for the formation of life and evolution to generate sophisticated life forms, since these stars have significantly longer lifespans. The first mission of JWST will study the TRAPPIST-1 planetary system, located around 40 light-years away from the planet. It revolves around a tranquil, red dwarf star and 7 small, stony planets. Despite having a much smaller, colder mass than our Sun, 3 of the rocky planets in the so-called habitable zone might contain liquid water on their surfaces. Due to its planet's close orbit, the TRAPPIST-1 star produces light that is similar to that of the Earth. The best chance for humans to see city lights beyond the solar system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun and our nearest star. Because Proxima is around 600 times fainter than the Sun, a planet must be 20 times closer to its furnace than the Earth is to the Sun for it to host life based on liquid water. In August 2016, astronomers discovered a planet with a mass of 1.3 Earth masses in this habitable zone. Proxima b may be an airless planet, given that it circles its faint red dwarf star Proxima Centauri at a distance of only 4.6 million miles. The distance between the Sun and the Earth is 93 million kilometers. Due to Proxima b's close orbit, it receives enough sunlight to maintain temperatures that are comparable to those on Earth and liquid water. The planet is also exposed to powerful solar winds that have the potential to destroy its atmosphere. Because of its relative closeness to the star, Proxima b is thought to be tidally locked, always presenting the same side of the star as the Moon does regarding the Earth. Nearby, there is a constant dark side and a constant sunny side. Regrettably, simulations suggest that the hemispheres of tidally locked planets may be susceptible to fast collapse when volatile gases freeze away on the night side. On planets with strong magnetic fields, these atmospheres are less likely to escape, although volcanic activity can also replenish the atmosphere. Since we are unable to determine Proxima b's volcanic activity or magnetic field strength, or if we were desperately trying to find out since an atmosphere implies the existence of seeds, and the two taken together imply the existence of life, we are unable to even speculate about the planet's likelihood of having an atmosphere. If Proxima b already has a sophisticated civilization, it may have solar panels covering the day side to generate power to light and warm the night side, which would otherwise be too cold and dark for a suitable life. Here, the JWST comes into play. The key to identifying the planet's atmosphere is its infrared heat signature. Additionally, the infrared portion of the spectrum has a strong attraction for Hubble's replacement. Therefore, Proxima b's night-side city lights may always be visible to the James Webb Space Telescope. If artificial light were limited to a frequency range that is 1,000 times narrower than starlight, humans could perceive it. Even if it were insufficient, our civilization relies on the night side of Earth's unique spectral edge and reflected starlight proximity for many of the technologies we use today. It will only take the JWST 11.2 Earth days to rapidly complete its orbit around Proxima b and detect the infrared radiation coming from both of its surfaces. We should pay close attention to the presence of gases like oxygen, water vapor, and methane in particular, since they may indicate the existence of livable circumstances, if not living things. One of the planned ground-based observatories that will conduct a thorough atmospheric investigation is the extremely large telescope, which is projected to begin operations in the middle of the 2020s. Comment below with your thoughts and let us know what you think.